All right. Sometimes when I'm doing statistics, I feel kind of like less than the sharpest tool in the shed, to use that euphemism, that analogy. I feel like, man, this is hard. Like, why is it hard? Why am I having a hard time understanding it? I think it's because it is hard. And I cite as support for that hypothesis, that theory, that it is hard. I cite the fact that statistics was taught at Harvard for 90 years before somebody decided to apply it to sports in the way that it was applied to sports, baseball, and it transformed the game of baseball and then transformed the way all professional sports are played. But it took 90 years before somebody was like, hey, let's apply this to how we put together a baseball team. 90 years. And that's 90 years of the smartest people on the planet taking statistics courses. And, it took 90 years. So it is hard. But sometimes I'm like, man, this is hard. Why? And I think part of the why it's hard is it's a little bit disjointed. So it's like, here's what you use in this situation, right? Like if you have to figure out inferences about the difference between two population means when the population standard deviation is unknown, or if you have to do hypothesis tests about the difference between two population means when the population standard deviation is unknown, right? It's a little bit disjointed. And it also has its own language. It's like a whole new language. How do you say sprinkled donut in French? Well, you got to go learn French. And same here with statistics. You have to learn statistics. You got to learn this language before you can even talk about it. There's like all this stuff. And so anyhow, I just went through this example and, went through it a couple of times. And then when I was going through it, I'm like, hey, what's D0 here? What's that D subscript 0 was one of my questions. And then also when I was going through this, it was like here it says, hey, negative alpha. I'm like, negative alpha? What are you talking about, negative alpha? And so I took all this and I put it into ChatGPT. And this actually makes me feel better about statistics. There we go. Let's just move that boy over. This makes me feel better about statistics because when I put it into ChatGPT, when I find errors, like, these are some of the, these academics, right? Like they're really high level statisticians and they put together this textbook and there's errors. There's errors in the presentation, there's errors in the textbook. So when I find those errors, I'm kind of like, all right, it's like I'm getting enough that I'm finding errors and able to point them out. And that's something that the people put together didn't see. So anyhow, regarding the minus sign in front of alpha, it should not be there. The alpha represents the level of significance in hypothesis testing, which is usually set to a positive value like 0.05. It is used to determine the critical value or p-value threshold, but there's no need for a negative sign before it. So that was it. And then also it was like, hey, what's the D0? And in the formula on the slide represents the hypothesized difference between the population means under the null hypothesis. Right, so we'll come back and read this in a second. And I'm going to say on slide, and which slide was this? Does it give me the file name? It doesn't. Example computer software package. On the slide that presents the example computer software package. Can you please solve that problem? Going through all of the steps and explaining them to me. So again, I'm just pointing this out here so that you see how to use ChatGPT to be like your tutor, and very, word to the wise, you should pay for it if you're going to do it, because the free model threw errors for me the other day. But I've never had errors with the paid model. So all good on that, which means, you know what? We're right at the very beginning of this new amazing tool that's been introduced to humanity, and we could use it in an extraordinary way. And I keep running across people who are really, really smart, and they have doctorates, and they're working at colleges and universities, and they're completely unaware of the power of AI and what you can do with it, and they have not integrated it into their lives yet. And so people get stuck in patterns of behavior and ways of doing things, and they don't change. And it's hard for them to change, even when there's a vastly superior way to do stuff, like, getting a tutor through ChatGPT to help you learn stuff, or checking your work, or checking the work of, you know, what a publisher put together. All right, so we're going to learn about, again, we're learning tools for different situations. It's a little bit disjointed, but here's this situation. You want to do a hypothesis test about the difference between two population means, but you don't know the population standard deviations. Rock and roll, man. Here's how you do it, right? Here's the test statistic. Here are your hypotheses that you could use. And so in this one here, we're going to see if a new, before you even read that, like I bring that up on the screen, and we just need a blank slide for a minute. Here we go. You ready? Oh, wow. Perfect. I got a blank slide perfectly. No, that's not blank. I got to get rid of all this stuff. All right, there we go. Blank. So before we even jump in and read all that, what I want to say is we're going to compare, in this problem, we're going to compare, there's like a current system, and then there's a new system. And we're going to see if the new system makes things more efficient. Okay, so here's the current system. Let's say it takes 4 minutes to do something. And if the new system takes 5 minutes, the new system's not better. If the new system takes 4 minutes, the new system's not better. It's still a status quo. So if the difference between these two, right, if 4 minutes minus 5, right, or 4 minutes minus 4, if the difference between these two, the current system, the new system takes 5, 4 minus 5 is -1. The new system takes 4, 4, current system, minus 4, new system, that's 0. So if the difference between these two means, when we measure how long does the current system take to do something versus how long does the new system take to do something, when we measure the differences, because this is the differences between population means, and our example, and I bring that up just to show you the difference between population means right there. And our example is going to give it, you know, it's going to go into that. But this situation, right, if we need to find out, hey, we have a current system, we have a new system, is the new system better than the current system, right? The current system takes 4 minutes, new system takes 5 minutes, new system's no better. So if we have the difference between these means, current minus new, 4 minus 5, we get a -1. 4 minus 4, current minus new, we get a 0. So our hypothesis is going to be if the difference between these population means, right, is less than or equal to 0, then that's our null hypothesis. But the opposite situation would be if the current system is here, and this is the new system, and the current system is taking 4 minutes, and the new system is taking 3 minutes, and if we take the current completion time and subtract the new completion time, 4 minus 3 is greater than 0. So our hypothesis is going to be like if the current minus the new is less than or equal to 0, current 4, new 5, 4 minus 5 is less than 0. 4 minus 4 is equal to 0, current new, right? Then that's the same situation. That's null, right? Nothing changed. That's the status quo. There's no change. It's the current state. And plus we put equality. We put equality into the null hypothesis. So that's going to be our null when we're looking for the differences between two population means. And then our alternative hypothesis will just be whatever's left, which is that the current, 4 minutes, and the new, 3 minutes, is greater than 0. 4 minus 3 is 1, which is greater than 0, right? So that's the alternative hypothesis. And so we're looking to see if something is less than 0, which makes this a right-tailed test. Did it go too high? Did it go too far out to the right? And what we're going to see is that, like, okay, here with 95% confidence and a right-tailed test, which means there's 5% here, 95% over here. And what we're going to see is that, hey, it did go too far. It went into this reject zone, right? Like these are the values that we ended up calculating. And that means we reject the null hypothesis. And so if we reject this null hypothesis here, that the current system, the mean, we're looking for the difference. We're looking for the difference between two population means. And so the mean completion time of the current system, let's say 4 minutes, and the mean completion time of the new system, let's say 3 minutes, right? That's going to be 4 minus 3, which is going to be 4 minus 3 is would be 4 minus 3. 4 minus 3 would be 1, which would be greater than 0, right? So the new is better, and so we're going to reject that. So it takes a little bit just to even wrap your head around how to do that bit. And to do this, here are different hypotheses we could do, and here you see that D subscript 0, which is the hypothesized difference, right? So coming back to this, the hypothesized difference between D0 represents the hypothesized difference between the population means, mu1 and mu2, under the null hypothesis. And so the hypothesized difference between the population means will be here, which is that it's less than or equal to 0, and we're going to need that, or it's greater than 0. And the hypothesized difference here will just be 0, that it's going to be 0. So it's kind of interesting that you have something you need to put into a formula, and the hypothesized difference is 0. But maybe at some point you might want to say, you know what, the hypothesized difference is 10 for whatever reason. So that's where you do that. And so here's the problem. You can pause the video, you could read it, but it's like, hey, current system, new system, is the new system better than the current system at a 0.05 level of significance? And we have 12 people using the current and 12 people using the new, and then we get all this data. And that's our sample size and the sample mean, sample standard deviation. So here's the data, 12 people. These are their completion times using the current system. 12 people, these were their completion times using the new system. And so you get all that, sample size, sample mean, sample standard deviation. And then here's the formula, and you plug all that in, and we fix that alpha had a negative in front of it. And you get this stuff. And so 40 and 44 are sample standard deviations. 12 and 12, those are our sample sizes. 325 and 286, those are our sample means, right? And then this is just 0. We get a t of 2.27. And so with a t of 2.27, we also have to know our degrees of freedom. So our degrees of freedom here, we use that formula again, plug everything in, and boom, we get 21. And so with 21 degrees of freedom, come over here, and here we have the z table, and here we have the t table, and they're just side by side, t distribution, z distribution, cumulative probabilities for standard normal distribution. I just think of it as z table, t table. But here we have the t table, and put them side by side just so you could compare them. We have 21 degrees of freedom, and our t is 2.27. So 21 degrees of freedom and 2.27, 21 degrees of freedom, 2.27 is going to fall right between these two, right? 21 degrees of freedom, 2.27 falls right between those two, right there. So that's between 0.025 and 0.01. And so if we come back here, we see between 0.025 and 0.01 is where that point is, and our t-value is 2.27, okay? And so we just map that on our line, and at p-value of 0.05, and with a t-table, you're looking at what's in a tail, right? What's in this top right tail here, you're looking at what's in that top right tail, whereas in a z-table, you're looking at what's in the left, from that point to the left. In a t, you're looking from this point to the right. And so with a z, we'd be like, hey, at this point, z, 1.96, we've got 97.5% of our data from here to the left, And then here we're saying, you know what, we got between there at 21 degrees of freedom, and 21 degrees of freedom, and you know, a t of 2.08. So from here to there, 2.08, we have 0.025 or 2.5% of our data from here to there, right? So that's the difference between those two. And so we get our you know, t-value, 2.27. We calculate that. And so that's like the t-value, 2.27. And then we also get our degrees of freedom, 21. So 2.27 with 21 degrees of freedom puts us, 2.27, 21 degrees of freedom, 2.27 puts us somewhere between these two, which means the area in the tail is between 0.025 and 0.01. So we're between 0.025 and 0.01. And we're setting up our reject area at 5%, 95% confidence level, 0.05 level of significance, 0.05 level of significance. So here, this is all 0.05. It's the reject area. We went too far. Our data is already out here. That's the p-value. But what is the t-value associated with that at 21 degrees of freedom? So at 21 degrees of freedom associated with 0.05, 21 degrees of freedom is 1.721. So that's our t-value right here at 21 degrees of freedom is 1.721. And so whether we use the t-value, the critical value approach, we could see that we exceeded that, right? That's kind of like our critical value. Did we go past that? This is our test statistic. They even call that the test statistic right here, test statistic, right? So that's our test statistic. And then here, or if we use the p-value approach, right, we want to do it to 95% confidence or 0.05 level of significance. And so that's 0.05 here. And we're at 0.025 to 0.01. And so we're going to reject the null hypothesis. And that's the same conclusion the book comes to. I think my little graphs are the more clear way. It's the more clear way, or however you say that, to come to this conclusion. But you could kind of look through their slides, which I'm going to show you right now. So you could, we did that one, we did that one. But I guess this is the only one we need. So you can pause the video and you can look through this slide and see if it makes sense to you. And now I'm going to move on. I like this one a lot better. So based upon all that, we can reject the null hypothesis. What we're rejecting is this, and what that means is that this, right? So if we have the current system, 4 minutes, and the new system is 3 minutes, 4 minus 3 is 1, that's greater than 0, the new system is better. So we could say with 95% confidence that the new system is better, right? The new software package provides a smaller population mean completion time. Right? So that's what we could say right there. And that's kind of a cool thing to be able to say. Like if you could calculate that and you could say, hey, the new software package with 95% better provides a smaller population mean completion time. And people will be like, you know, they'll look at you like, wow, you actually learned statistics? Like if you were to bust that out in a meeting, people would be like, right on, you know, like I'm serious. Like nobody ever in my professional life has done that. And if you can do that, you're going to change baseball or something else, right? Because people don't understand statistics. I think most people don't understand it, and they don't understand it in a practical way. Like, how do you actually use it? You know, enough of this like academic jargon. Like, how do you actually calculate stuff so you can make some money? That's what I want to know. All right, so that's that one, and in the next video, we're going to do the next one. See you in the next video.